Hey everybody, this is Dr. Wood and I'm going to be covering your Biostats review today. I know this is a highly anticipated video for many of you. Hopefully you've reviewed all the videos up to date, gone over the stuff we've covered in class and are ready to rock this quiz. I think you're all going to do, or I'm sorry, rock the test, I should say. You're all going to do quite well. If I were to guess, I think it would be highly probable that you're all going to do awesome on this test. But anywho, but yeah, so what I would recommend is certainly reviewing everything, getting, make sure you have a pretty good understanding of the topic at hand, and then go through the quiz along with the recording if you like. So that way it'll be kind of like the Kahoots we normally do. I'll go through the question and then get to the answer pretty quick, so you may want to pause and really think about the question, see how you would come up with your answer, see if it's correct or not, and then go from there. On the PowerPoint that I've uploaded with all the questions here, you will find that the answers are down in the notes section, including any other, ancillary comments that might be there, maybe further elucidating some of the, points about questions I may or may not ask, etc. So anyway, so let's get to it. Let's talk about some biostats review questions. So question one's getting back to definitions, which are some questions on the test are certainly going to be covering the definitions since this is a new topic for many people. We want to make sure those definitions are certainly down. So the first question here is, what is meant by standard error of the mean? Is it A, an estimate of the standard deviation of a group of sample means around the population mean? Is it a measure of the frequency of an occurrence over some time interval? It represents a relationship between specificity and sensitivity, or it's a mathematical equation to convert non-symmetrical data into a normal distribution. And so, based off of this, going back to thinking about things like standard deviation, standard error of the mean, think about things like confidence intervals. This kind of goes back to specifically the definition for standard error of the mean, just meaning it's an estimate of the standard deviation of a group of sample means around the population mean. Basically, what this is trying to get at is saying that if you have a sample taken from a population, so say for instance we're wondering about the average temperature of everyone in the US. Let's say, for instance, that average is 98.6 degrees Fahrenheit. If we were to take our sample out, our sample is going to have some variation in it. You may find that that particular sample, especially if you only take like 30 people, as opposed to the entire population of millions, you may get something like 97.6, right? And so you would end up getting a standard error of the mean that would show, okay, well, kind of how close would this standard, our standard deviation be kind of around the standard, kind of the mean of the entire population. So kind of how close are you going to be getting to that actual population mean? And so this is one of those big ones that gets directly influenced by sample size. So as you increase the sample size you have there, that n, as it gets larger, you're closer and closer representing the entire population. So if you took that sample size, say from 30 and then blown it up to say like 1 million, you'd be a whole lot closer as far as averages go, mainly because a lot of the outliers would cancel each other out to getting to the actual population average there. And again, most of the time you're not going to know the population average, but at least it gives you some kind of idea, kind of how close you're going to be getting to that. Okay. And so all these other definitions would not be correct in this case here. Certainly things like, a measure of frequency of an occurrence over some time interval. It's usually some kind of like frequency chart or like a frequency analysis, so it would not be representing standard error of the mean. The relationship between specificity and sensitivity. It's not really a good term for this, so to speak. But again, that's where we're going to get into like likelihood ratios and positive predictive values and things like that we discussed at the last session. And then a mathematical equation to convert non-symmetrical data into normal distribution. That's basically where you have like a log normal distribution, where it kind of looks asymmetrical, but then when you convert it over, you'll end up finding that it does more closely represent a normal distribution. So again, a lot of times you can't just look at a graph and know whether something is normally distributed or not. There's a lot of math that goes into finding out if that is the case. Next question. Suppose a clinically accepted value for a mean fasting glucose in females aged 20 to 29 is 100 milligrams per deciliter, and the standard deviation is 10 milligrams per deciliter. The fasting glucose for a 25-year-old female was 130 milligrams per deciliter. How many standard deviations above the mean is the subject's fasting glucose? So is it answer A, 5, B, 2, C, 1, or is it D, 3? Okay, so looking at this, and again, kind of thinking back to your graph here of your normally distributed set of data, remember that we're thinking the bell-shaped curve. How does that kind of, where are we thinking as far as what the answer is going to be here as far as the standard deviations go? Well, the answer is actually going to be D. This would be a patient who would be 3 standard deviations above the mean fasting glucose here, okay? And so to relate that back, let's go ahead and do a very poor drawing, as you're going to see here. So we're going to say here's our graph, here's our normally distributed set of data. So sort of bell-shaped curve, as close as I could get to it. And again, remember, here's our mean value. So in this case here, which again should be right through the middle, is going to be 100, okay? So the value here is 100. As you go a standard deviation up, and we said the standard deviation is 10 milligrams per deciliter, as you can see here, you're going to go up one, right? So now we're at 110. Now we're at 120. And then one more standard deviation up, we're at 130. So this is where our patient would be right here, having a fasting blood glucose of 130. And again, remember that as you get further and further away from that mean, you're finding that there's fewer and fewer people that will have that extreme of a value there, right? So again, most people are going to be around 100. As you get further and further away, you're going to find that a fewer number of people will have a value of 130 or less. Right, so we'll get into the actual percentages there in just a few minutes with one of these other questions, but really figuring out how many standard deviations the patient is away is as simple as that. So just looking what the mean value is and seeing kind of how far away you are. Okay, the questions maybe get a little bit more complicated than this, again, when you're kind of looking at more specifically how you're applying this information, but at a bare minimum, you should be able to figure out, okay, how many standard deviations away is my patient from, say, the mean value, okay? Question 3. In statistical analysis, an alpha or a type 1 error refers to which of the following? Is it A, the probability of rejecting the null hypothesis when it is true? Is it B, the probability of failing to reject the null hypothesis when it is false? Is C, the probability of keeping both the null hypothesis and the alternative hypothesis when neither is true? Or is it D, the probability of rejecting both the null hypothesis and the alternative hypothesis when both are true? Okay, so going back, you have to know what the null hypothesis is to know kind of what you're talking about. So in this case, the null hypothesis is there's no difference between my groups that I'm comparing, right? So again, if I give a new drug to a patient, to a group of patients and give placebo to the other, the null hypothesis says there should be no difference in blood pressure after giving that medication, okay? So the question is, when can I reject that? And that's where you do your statistical tests. That's where you would think about your p-value and things like that. Now, again, there's two different types of errors we referred to, type 1 and type 2. Type 2 being more referred to as sort of like a beta error. But in here, we're specifically referring to the type 1. And so in this case, the answer would be A, the probability of rejecting the null hypothesis when it is true. So again, basically what that's saying is you're saying that yes, there is a true difference between the groups. The medication I gave to my patients made their blood pressure lower when actually it was not the case. Okay, so what we're saying is that actually the null hypothesis is true. There's no difference between the groups, but we rejected it anyway. We incorrectly rejected it. That's a type 1 error. That's a false positive error. You said there's a difference when really there isn't one. Okay, now on the flip side of that, type 2 error is saying there's no difference and you keep the null hypothesis, but there actually is a difference, right? And again, what we said there was typically it means that your study was underpowered. You didn't have enough people to actually show the difference that was really there, okay? So again, it's critical to know the difference between type 1 error and type 2 error. Type 1 is false positive, type 2 is more of a false negative. So let's say we have a clinically accepted value for mean systolic blood pressure in males aged 20 to 24, and it's 120 millimeters of mercury, and the standard deviation is 20 millimeters of mercury. Okay. Now, what proportion of readings are going to lie within the ranges of 80 to 160 millimeters of mercury? Would it be 0.9 or 90%? Would it be 0.95 or 95%? Would it be 0.6 or 60%? Or would it be 0.99 or 99%? And so the question here would actually be B. 95% of the values would fall within the range of 80 to 160. So again, let's draw a very poor bell-shaped curve here. Let's look at that. All right, so let's say our mean value is right here, and it's going to be 120 millimeters of mercury, right? And we said And again, I can try to write this in. Again, I'm using my right hand on a mouse, and so this is going to be, actually that's probably better than my normal handwriting, so there you go. Anyway, so let's look at the values in either direction here, right? So again, imagine that I went one standard deviation out in either direction. And because my standard deviation is 20, I know that the one standard deviation to the right would be 140. And a one standard deviation negative, or going to the left here, would be just 120 minus 20, right? So it'd be 100. So that's one standard deviation out, right? And if you recall, one standard deviation either direction, this should actually, from this basically from here to here, should be 68% of your values, okay? So about 2/3 of all your values should fall within this range of one standard deviation in both directions, okay? Now we said, okay, well, we wanted to figure out the range within 80 to 160, so we're not far off and out yet. We have 100 to 140, but so we need to go further out. So this is where we're going to go one more standard deviation out in either direction, right? So again, this is where you're going to go down here. You have another standard deviation here, and so at this point you have 80 and you have 160, right? So that means that now we have our ranges here, right? So now we know that to get the range of 80 to 160, we had to go 2 standard deviations out from the mean, okay? So 2 standard deviations, we know that one standard deviation in both directions actually ends up being 68%. Well, when we do this, when we have 2 standard deviations out, this is actually going to be 95%. So this is why B is the correct answer. So we know that if we have a patient and their blood pressure value falls somewhere within 80 to 160, we know that there's probably going to encompass about 95% of patients we may encounter. And again, that's only referring to male patients aged 20 to 24, that roughly 95% of them should have a value systolic blood pressure between 80 and 160. Okay. Now the question is, well, what if we even went more extreme? Let's say we went out for 3 standard deviations. At that point, we said, well, what are the percentage of individuals, male patients between 20 to 24, that would have a systolic blood pressure, say, between 60 to 180? Now, that's a huge range there, so we should be able to capture more of those individuals. And so now when you go from 2 standard deviations, which is 95%, and go to 3, that's where you're going to be getting more of those outliers, and that's where you're going to get roughly 99%. So you can go 68, 95, and then 99%. So again, by 3 standard deviations out, you should be getting almost everyone. However, there will still be some outliers, but there won't be very many at that point. Okay. And wouldn't you know it, accidentally gave away the answer to the very next question. So, I thought I made some pretty good points in the last slide, so I'm not going to go back and correct my recording here. But let's say question 5, using the empirical rule, which is what we're using in the last question there, what percentage of observations are going to lie between plus and minus 3 standard deviations of the mean? And again, we said when you go out, here the answer choices being A, 40%, B, 68%, C, 95%, or D, 99%. The answer here is being 3 standard deviations out, we have 99%. So the answer here would end up being D. Again, if you only go 1 standard deviation, that's going to be 68%. If you go out 2 standard deviations, that's going to be 95%. And again, 3 standard deviations is 99%. All right, up next we have question 6. If significance level, or our alpha, is being set at 0.05 and we have a p-value of 0.1 that's obtained as a result of a study, what does this indicate? Is it A, the results of the study are statistically significant? Is it B, the results of the study are not statistically significant? Is it C, we're unable to determine whether results are statistically significant? Or D, the results of the study are more reliable than expected? Well, based off of this, it would say that the value of 0.1 is above our alpha of 0.05. So we're going to conclude that the answer is B, the results of the study are not statistically significant. Okay. Again, this doesn't tell you anything about the effect size of what you found. It doesn't tell you how much the blood pressure dropped. It doesn't tell you how much the temperature increased. It doesn't tell you anything about the actual effect size that you were studying. It only tells you about the statistical significance of the value here, right? So again, how likely are the results that you found just due to random chance versus there actually being something there. There actually being something that's moving your data one direction versus the other. Okay. Now again, we cannot determine anything about clinical significance off of this, right? With clinical significance, you actually have to look at the values to see, okay, well, hey, my blood pressure dropped 20 points. That's pretty good, right? Versus if it was just 2 points, not so great. Either can be statistically significant, but one is much more likely to be clinically significant here. Okay. Now again, if you were to run this test and you had your p-value 0.1, now the question is, okay, well, am I making a type 2 error or not? We said a type 2 error is where you're going to be keeping the null hypothesis, right? We're not going to reject it, but we're going to say, well, there actually was a difference there, but in oftentimes those cases when you make that type 2 error, usually it's going to be an issue of sample size, right? So if you have more people, chances are you'd be more likely to find that difference. All right, so the question here is the width of a confidence interval is influenced by which of the following? Is it the standard error of the mean? Is it the p-value? Is it the sample size, or is it the F ratio? Here, the correct answer is going to be sample size, C. Right, so again, the width of that confidence interval is directly influenced by this. So typically, the bigger the sample size you have, the less scatter in the data there's going to be. Typically your standard deviations are smaller. You're going to find that that is going to help to narrow up that confidence interval. So that way you have a much better idea. You can be much more confident when you say, hey, I think the actual value, if I were to say apply this to the population as a whole, would be somewhere between this and this. That range can get much more narrow. So say, for instance, you were looking at doing, say, a blood pressure study, and you say, hey, this intervention went ahead and dropped the blood pressure, say, by 20 points on average, right? So our mean value there dropped the blood pressure, and our sample was, say, 20 points there. Well, if we had only had a sample size of, say, 30 people, you might have a confidence interval that ranges between, say, reducing the blood pressure by 5 millimeters of mercury, and could range all the way up to, say, 40. Well, if I had more people, right, and you had a better representation of the whole population, say, and now we're looking at a study of 3,000 people, you may find you get the same average. You may still get that same average of 20 points drop in blood pressure. However, you're going to be able to say, well, I'm much more confident about the actual value if I were to apply this to the population. And so those confidence intervals do narrow. And say, instead of going from 5 to, say, to 40, it went down, and now it's, say, 18 up to, say, 22. It can narrow down pretty significantly by increasing your sample size. Okay. Next up, you're reviewing a survival analysis study in a medical journal, and you astutely note here the study has about 200 individuals enrolled in the study, and the study ran for 10 years. Okay, and we're going to say this is kind of an unusual study because everyone kind of got in all at the same time. At the end of year 2, we had 177 subjects that remained in the study. At year 2.9, there's 165 subjects remaining. At year 5.8, there was 100 subjects remaining. And then at year 10, we had 75 subjects remaining. Now, the median survival time for the study is which are the following. Is it A, 2 years, B, 2.9 years, C, 5.8 years, or is it D, cannot be determined from the data that we have here? And so the answer here is actually going to be C, 5.8 years. So the reason for that is, and the easy way to do this, is that the fact that we're looking at median survival time. This is survival analysis, pretty basic stuff here. So again, median survival time. Now, we will know we hit the median, which is the median value, which means that when we lose 50% of those patients or get basically down to that middle value, in this case, we started out with an N of 200. We say, well, what's 50% of 200? 100, right? So at year 5.8, we got down to 100 subjects. That's going to be our median survival time, okay? Now, the other question is, why do we look at median survival times? Why don't we look at average survival times? Well, the reason for that is that to get an average survival time, you have to monitor every single person to see how long they survived, right? So again, your study would have to probably run for a whole lot longer than 10 years. And so again, if that's not very feasible based on the study protocol that you design, you're not going to really get a good mean because a lot of people may still be alive. That will skew your data pretty significantly. By at least getting to the middle point where I say, okay, well, 50% of my subjects have died or dropped out, that's when I know I've hit the median survival time. And it makes it easier to compare different studies together when you're looking all at median survival times. So here, it's very easy. Just look for the 50%, or that time point where you get to 50% of your starting in. And at this point, it was 5.8 years. So which of the following variables is spaced with equal intervals or distances and the 0 point is not considered meaningful? 0 point is not considered meaningful. Would it be an interval variable? Would it be a continuous variable? Would it be an ordinal variable? Or would it be a ratio variable? The question, or the answer here is it is an interval variable. Okay, so this is something like temperature where you can actually go down to negative numbers and the 0 actually doesn't really matter. Now, the reason why that's important is because with the interval variables, you really can't do ratios with them. You can't divide one interval variable by another one because the 0 point doesn't matter. So the math doesn't really make sense in those cases there. However, what you can do when you have something where the 0 point is significant, right? So again, imagine if you're dealing with like blood pressure, you can have zero pressure. You wouldn't have negative pressure necessarily when dealing with blood pressure. So at those points, that's where that turns into what we call a ratio variable, and then I can do ratios of one divided by another, right? With interval variables, I can certainly subtract one from another. That's okay. That's totally fine. But with ratio variables, you can get a little bit more sophisticated in the type of analyses and comparisons you can do, okay? Now, both interval variables and ratio variables are a type of continuous variable, and the important part with the continuous variable is that there's that equal intervals or distances between each point, right? So as I mentioned, the differences between a temperature of say 1 to 2 degrees Celsius is the same difference as 99 to 100, right? So because of that, those are continuous variables. If you don't have an equal interval distance, or if say it's unknown, that's when you start to get into ordinal variables. So that's when you get into things like, your pain scale from 1 to 10. While that may seem like a continuous variable, with something as subjective as pain, you find that someone's 10, the difference between 9 and 10 can be very different between individual patients, right? Or the difference between a 3 and a 4 can be drastically different depending on who you're talking to. So another example would be those Likert scales when you do your evaluations for your professors and you say, I strongly disagree, I somewhat agree, and I strongly agree. Again, there's not a defined distance between those, and they may not all be equal. So because of that, that's considered an ordinal variable. Okay. The other one would be nominal variables, where again there's no actual difference. There's no defined difference between the two. Not one's better or one's worse, and that's when you get into like categories of things. So if you say Ford versus Chevy, if you say man versus woman, if you say red versus blue, those will all be considered nominal variables. The next question here is which statistical test is best used to summarize a case control study? Is it A, relative risk? Is it B, odds ratio? Is it C, chi-square goodness of fit test? Or is it D, survival analysis? So first question you have to ask yourself is, well, what the heck's a case control study, right? So figure that out, and then you should be able to figure out, hopefully, what the statistical test would be that's going to be appropriate for this, okay? And so the answer is B, odds ratios. And so here the question is, okay, well, why am I using an odds ratio versus say something else like relative risk versus say chi-square? And again, it goes back to knowing specifically what the tests are good for and maybe what they're not so good for. So let's go through each one of these. So looking at an odds ratio. Well, going back to what kind of study we have, it's a case control study. And if you remember, with case control studies, you're starting out with people who have the disease you're actually interested in or the outcome you're interested in. Those are your cases, right? So if you have lung cancer and you're looking at exposure to smoking, the cases are people who have lung cancer. And you're controlling that by comparing it to people who do not have lung cancer, right? So you're taking a group of people who are similar to your cases, right? Either in age or gender or other comorbidities, things like that, and comparing them to your cases. And then you're looking retrospectively, right? You're looking back in the past to see what their exposure was to say something like smoking or say to drinking or whatever the case may be. So by doing that, you're looking backwards. You don't really have a full set of like, well, who all would have been actually at risk for lung cancer. Like, so for instance, those controls you pick, not all of them may have actually been much at risk for having lung cancer in the first place, or we just don't know. So because of that, we can't really know what our full denominator is going to be. And I'll show you an example where that is going to be the opposite in just a second. But you don't really know what the denominator is. So because of that, we have to use the odds of something happening versus not happening. And that's where you switch from using the probability, where you have a full idea what your denominator is, to moving over to odds. And so basically you just take the people that got the outcome divided by people that didn't have the outcome, or people that had the risk factor divided by people that did not have the risk factor. And so those give you odds. And if you remember, when you're dealing with probabilities, they can range from say 0 to 1 or 0 to 100%. With odds ratios, it's usually anything over anything above 0, and it can go up to infinity, right? So you can have a very high numerator, very small denominator, versus with probabilities, you're only dealing with the range from 0 to 100%. Okay, so odds ratios are going to be good for retrospective studies, and case control studies is a good example of that. Okay, now relative risk. This is where you're going to be dividing the risk of one thing happening divided by the risk of happening in a different group. So these are going to be good for, say, like an experimental study where you're going forward in time. So you have a prospective study, and you're looking at, say, the cardiovascular outcome for people taking aspirin, say, versus not taking aspirin. Now, note here we are setting up whether the people are getting aspirin or whether they don't get aspirin, and because of that, that's why it's an interventional study, because we're, as the researchers, are making that we're actually making the intervention there. And you're looking prospectively because we started the study at point A and we're kind of going forward in time. So it's a prospective study there. And then in those cases where you're looking at the denominator, well, we're setting up the number of people who are in each group. So if we say 100 people will get the aspirin and 100 people do not, that's our denominator. We know what that's going to be from the start of the study to the very end. Our denominator is always going to be 100. So based off of that, you would then go forward in time, see your outcomes. Say you had 40 people die of cardiovascular death in the non-aspirin group, and you only had, say, 18 die in the aspirin group. You're still dividing that by 100 because that's your denominator there. And so in that case, you're using probabilities, and that's why the risk is going to be from 0 to 100%, because you are, again, that denominator is going to be the number of people who had the outcome divided by the total sample size, right, in those cases there. So that's why relative risk is better for those prospective sort of studies. Odds ratios are better for the retrospective. Chi-square goodness of fit tests are typically good for nominal data or ordinal data, where you're basically trying to look at frequency distributions and seeing, are things happening just due to random chance, or the values that you're getting for each category different enough to where it's very unlikely to be due to random chance. Okay. And then survival analysis, we mentioned, is going to be good for looking at things that have a very defined outcome. Usually a one-time and you're done sort of outcome, like death. You can only die once, unless you're James Bond, I suppose, but you can only die once. And so in those cases there, that's where we're using things like median survival times, but you have to know the time that it took to get from point A, where they entered the study, into where the actual outcome occurred, right? All right, for question 11, a researcher is seeking a statistical test that can determine whether the means of several groups are all equal or not. Which of the following would be the best test this researcher should select? The question is, would it be A, ANOVA test? Would it be B, a two-sample t-test? Would it be C, a Mann-Whitney test? Or D, a Wilcoxon test? So, the question is, what kind of test are we going to use when we're looking at multiple groups here? Again, trying to figure out if they're all equal or not. So is it A, ANOVA, B, two-sample t-test, C, Mann-Whitney, or D, Wilcoxon? Well, the answer actually is A, ANOVA test. Now remember, the ANOVA test is good for comparing 3 or more groups together, right? So again, if you're looking for a difference anywhere between those groups, again, it's not specifically saying where the difference is, it's just saying there is a difference between at least one or more sets of groups. Or they're just all the same, right? And in that case, the null hypothesis would say there's no difference between the samples there. So that would be good for that multiple group. So the answer would be A here. B would be a two-sample t-test, is going to be used when you're just comparing 2 groups together. This is also known as a student's t-test typically. So again, you would not want to use it for more than 2 groups. And then Mann-Whitney and Wilcoxon tests, those are going to be non-parametric tests. Those would be used for non-parametric data or non-normally distributed data. Unless I put it on the test specifically that's not normally distributed, you can just say that it's going to be a Gaussian distribution, normally distributed. Again, most oftentimes I'm going to put that yes, it is normally distributed, but again, I'm a human, I'm prone to error just like anyone else is. So again, that's an assumption you can make on my test. I will tell you very specifically if I'm looking for a non-parametric or non-normally distributed test, that's what I'm looking for. Next up, a laboratory test that correctly identifies patients with a disease state is said to be which of the following? Is it accurate? Is it specific? Is it sensitive? Or is it negative? So again, the laboratory test is correctly identifying patients with a disease state. So they have the disease and we're correctly identifying it. Okay, so the answer here, it would be C, sensitive. Again, sensitivity is referring to being able to pick up the disease state when it's truly there. Specific is being able to say that the disease is not there when it truly isn't, right? So again, you're looking for the true negatives with specificity. With sensitivity, you're looking for the true positives. Again, hopefully our tests are accurate, but it's kind of using a different metric there, not really what we're talking about here. And then negative, just obviously the term we use when things are negative. It's when they come up as being a no. For question 13, calculate the likelihood ratio for tests with a sensitivity of 90% and a specificity of 55%. Now again, am I going to have you calculate this on a test specifically? No. But what I would like you to at least have an idea of is how do we actually get to those likelihood ratios? What are the things that actually go into it? What can they actually tell us about the different tests there, right? So again, looking at this, we have either A, 0.5, we have B1, we have C2, or we have D, 5.5. The answer here is actually C2. So what this is trying to say, and if you get back to the likelihood ratio, basically it ends up being calculated as your sensitivity divided by 1 minus your specificity. Again, we're going to get more into detail on this a little bit later on. This is kind of just introducing the concept. But if you were to look at this, we would basically be taking 0.9 or 90% divided by 1 minus 0.55, or in that case it would be actually be 0.9 divided by 0.45. And so that actually ends up equaling out to be 2. You can do the math if you like to double check me there, but likelihood ratio actually ends up coming out to be 2. What that means is when you're actually applying it to a patient, if you get a positive test result back, that means you're 2 times as likely to actually find that that's a true value. That is actually likely to be the case, that that's a true value with that patient there, right? Again, a low likelihood ratio. So say for instance you had something like 0.5 would mean that it's not very likely to actually be the case there, right? So if it was 0.5, that would really mean that it just because it comes back positive doesn't mean the patient actually has the actual disease state there. So going back to the example we used in class, I think one of them was using different symptoms related back to diagnosing appendicitis, right? So for instance, having something like abdominal pain, which is not super specific for having just appendicitis, it could be anything, would probably have a pretty low likelihood ratio. So just because it was positive doesn't actually mean that the patient has appendicitis, versus something like right lower quadrant pain, which is much more specific for being appendicitis, would have a much higher likelihood ratio. The sensitivities and specificity would be much better, be much more likely to show that yes, if you do have right lower quadrant pain, you're much more likely to have a true diagnosis of appendicitis. All right, so the next question is, which of the following is a nonparametric test used to evaluate non-paired data? So, okay, so we're already looking at nonparametric, we're thinking non-normally distributed data, and we're looking at non-paired data here, okay? So would it be A, Wilcoxon signed rank test? Would it be B, the Spearman's rank correlation? Would it be C, a linear regression? Or D, the Mann-Whitney U-test? So the correct answer here is D, the Mann-Whitney U-test. So, looking at these different options here, so Mann-Whitney U-test again is a non-parametric test. So again, this does not make the assumption that the data is normally distributed, and then it also is going to be comparing 2 samples together, right? 2 different groups together, but they're non-paired, which means they're going to be independent samples from one another. Now the option you would have selected had I said paired data would have been the Wilcoxon signed rank test. So you have 2 groups of patients who are say related to one another, say they're brothers or sisters, say you're measuring the same person multiple times, that would end up being a paired data, and you'd use the Wilcoxon signed rank test. Okay, linear regression is where you're going to be trying to find the best fit line and you're figuring out how much of that kind of that variability can be predicted from one dependent variable from an independent variable. That kind of goes back to looking at the incidence sensitivity example that we had a couple of lecture periods back. And then that Spearman's rank correlation, that's where you're actually finding that R squared value, where it's actually kind of telling you how much of the variability in the dependent variable is being explained by the independent variable. Which of the following tests is used to assess the observed versus expected findings of a study? This would be a paired t-test, an outlier test, a normality test, or a chi-squared goodness of fit test. The answer here would be D. So this kind of goes back to what we were talking about earlier when you're dealing with, say, nominal data, or if you're dealing with ordinal data, again, where you're just kind of putting things into categories. You're looking at them and you're looking to see, okay, well, what's the observed frequency? And then based on what you're actually, how you're categorizing people that pop up in your study, and then versus the expected findings. So again, what would you have expected just due to random chance by itself? And you look to see how big of a difference there is between the observed versus the expected, right? And again, you're just looking at the frequencies, and that chi-square test will give you a p-value. And basically, if it's less than 0.05, if that's what you set your alpha to be, that just means that the actual observed frequency is unlikely to be due just to a random chance alone. It appears that there would be a very low probability that's just due to chance based on how extremely different the findings are in the observed versus the expected here, right? With a normality test, that is just looking to see if your data is normally distributed or not. With the outlier test, is looking to find if a value is truly an outlier or not. And then with the paired t-test, that's where we're going to be using paired samples. In this case, it would actually be a parametric test or normally distributed data if you're comparing two samples together that are paired, right? That's a siblings example, or if you're measuring the same person more than one time. Up next, which of the following statistical analyses finds the line that best predicts y from x? Would it be linear regression, nonlinear regression, a chi-square goodness of fit test, or a normality test? Again, I've already talked about several of these, but in this case, the answer would be A, linear regression. Again, this is where you're basically getting that the equation for the line, and again, that insulin sensitivity example is a good example of that, where you're looking to see how much of the dependent variable, the y, is predicted from x, right? And again, it matters which one is x, which one's y. Typically, you want your dependent variable to be the y. Your independent variables are going to be on the x-axis there. Okay, linear regressions is just use a very simple straight line. More complicated, you can get to nonlinear regressions, which is kind of outside the scope of our talk here. And then obviously we've talked about normality tests and chi-square tests already. Question 18, which is the most sophisticated method of data measurement? Ordinal, nominal, ratio, or internal? The answer here would be C, ratio. I alluded to this again pretty early on, first couple of questions. Again, when I say sophisticated, meaning how complicated of statistics can I actually apply to the actual measurement, right? When things come up as nominal, they're either yes, no, red, white, blue, anything like that. Like you can't really do a whole lot with that. I can look at the frequency, but I can't do things like means. I can't do things like, risk assessments and risk ratios and things like that. So nominal, ordinal, more the least sophisticated. Nominal being the least, ordinal being kind of a step up from that. Internal is not actually what we talked about. We talked about interval. So that would not be correct there. But then ratio, yeah, that's where that 0 point is. It's a type of continuous variable where the 0 point is significant, or where it's you can't go below 0 necessarily. And so those are going to be great because you can do ratios. You can divide one from another and start to get some analyses done via that. So that's why we call it the most sophisticated. You can do the most number of sort of analyses on it. Which of the following study designs is generally accepted as the most reliable evidence that a treatment is effective? A case control study, a cohort trial, a randomized controlled trial, or a case series? And the answer here would be a randomized controlled trial. So again, oftentimes with a lot of the data that we're seeing in the medical literature is looking at things like correlations. Finding actual causation is much more difficult to do, right? Because again, to say like, yes, this caused this to occur, you gotta be really sure about that. And your study design really needs to show that. So in this case here, where you're doing things like observational trials, where you're just looking to see kind of what's happening without you doing anything, that's going to give you some amount of an idea about cause and effect, but it doesn't really give you the most reliable evidence of that, right? So the case control study, that's where we talked about, getting your cases with the outcome that you're interested in, and then controlling them with people who don't have the outcome, and then looking backwards in time to say, what sort of risk factors may they have been exposed to. So again, yeah, people with lung cancer had a higher propensity for them to be smokers. Does that mean lung cancer is caused by smoking? In that sort of study, no, you couldn't say that necessarily. You'd have to use something like a more large prospective trial that would give you more credence, more reliability in thinking that yes, this actually caused this. Cohort trials would be where you would, another type of observational trial where you would take people and divide them up based on their exposure to the risk factor. So in this case, say I was going to say, well, I'm going to look at smokers and then look at non-smokers and then go forward in time and see who develops lung cancer. That's going to give you a little bit better sense of like, yeah, okay, the lung people that were smokers, way more of them got lung cancer. That gives you a much better idea that, okay, well, it looks like this actually caused this. The best way to do it, though, would be if you had a randomized controlled trial where you say, okay, I'm going to take this 1,000 people here. I'm going to make you guys smoke 1 pack a day for 10 years. I'm going to take this group of people who are going to be the non-smokers and follow you for 10 years, right? Now, of course, that's an unethical trial. No one would ever do that. But that would give you a very clear idea that, yes, Lung cancer was more prevalent in the group that was smoking. Thus, we have a very good idea this is a cause and effect sort of thing. Smoking causes lung cancer, right? Case series is just where you're looking at a group of individual cases that may have actual no relationship to one another. Again, those can be useful to try to illustrate maybe kind of an interesting point or sort of a new phenomenon, but really can't get a whole lot of good cause and effect information from that. For question 20, which of the following tests makes no assumption about the population distribution? It would be parametric test, nonparametric test, chi-square test, or normality test. Here, this would actually be B, non-parametric test. Again, this is where you're taking away that assumption that your data is normally distributed, and so that's why we end up using non-parametric tests in those cases there, right? We're not making an assumption about the population distribution. That does make it harder for our statistical test to achieve significance and get to a p-value less than 0.05. However, that makes our data more robust, meaning that we can be more confident that, yes, if we did actually find a difference, that actually is true. We're unlikely to make a type 1 error, less likely to make a type 1 error because of a false assumption about the population distribution. Okay, so this is a little bit more complicated because this is where you actually have application of the information here, and you're trying to make an assessment based off of what you're reading in the vignette. So, question 21. You were reading an article in which the investigators wanted to compare treatment with a new diabetic medication versus placebo on fasting blood sugar. The researchers randomized 40 patients to either receive placebo or drug X. The researchers then used a paired t-test and found that the patients in the experimental group had a mean difference in fasting blood glucose of negative 10 milligrams per deciliter with a confidence interval of negative 21 to 7. Which of the following conclusions would be correct? So it would be A, the results are clinically and statistically significant. B, the researchers may be making a type 1 error. C, the researchers are using the paired t-test correctly. Or D, the researchers may not have enough power to reject a null hypothesis. Okay, so the actual correct answer is D, but let's work through and see why each one of these are either correct or incorrect here, okay? And again, this is going to take a little bit more application here, so you have to kind of think about each of these individual answer choices and say, okay, well, is this actually true or not? And if it's not, then you go ahead and reject it and say, this is not going to be the right answer for this question here. So let's look at part one. Okay, so the results are clinically and statistically significant. Okay, so whether or not something is clinically significant, that is very much dependent on the provider and kind of what you think tend to be clinically significant, right? So again, looking at the mean difference here, being a negative 10 milligrams per deciliter, I mean, maybe that's clinically significant, maybe not. Like, 10 milligrams per deciliter, not a big deal, right? Maybe if you're going from, say, 120 to 110, but if I got a patient who's running, a blood sugar of, say, 200, going down to 190 doesn't make that big of a difference there, right? Or at least when you're comparing the two treatments together. So in that case, I probably would not say it's clinically significant, but the more important thing here that we can actually definitely determine, which is objectively true, is whether or not this is going to be statistically significant. And so one thing you're noting here is that we're doing a difference, a mean difference. So we're taking one mean and subtracting it from another, and we get that value of negative 10. And then looking at the confidence interval, we see that it ranged from negative 21 all the way up to positive 7. And if you remember, when you were evaluating confidence intervals for risk differences or differences in the means, if you cross 0, that means that you do not have a statistically significant finding. Okay. Again, because if the answers are the same, say, the means are 40 minus 40, and you get 0, that means there's no difference, right? So that's why 0 is going to be our level, or kind of our cutoff point for significance here. So because the results went from negative 21 up to positive 7, that crosses 0, we can automatically say that this is statistically not significant. We could rule out A as being a correct answer, okay? Moving on, the researchers may be making a type 1 error. So based off of this, what is a type 1 error? Well, let's say I'm going to reject the null hypothesis when there's not actually a true difference there. And so looking at this, they did not find a statistically significant answer here. So again, negative 21 up to 7, they didn't find a statistically significant difference. So they cannot reject the null hypothesis. Thus, they cannot make a type 1 error. To make a type 1 error, you have to actually reject the null hypothesis, right? So B would not be correct. C, the researchers are using the paired t-test correctly. So look at the type of patients we're doing. Look at the comparison here. They just randomized 40 different patients into receiving either the drug or the placebo. There's no relationship between these patients, and thus they're independent samples. And so you do not want to use a paired t-test in that case here. So they are using a paired t-test incorrectly. They should have used an unpaired t-test. And then finally for D, the researchers may not have enough power to reject the null hypothesis. Here you found that they did not have a statistically significant finding. So that means that, and again, assuming they use the correct type of t-test in the future, they may need more patients, right? 40 patients, and again, dividing those up into two groups with 20 in each, hard to really find a statistically significant difference there, right? Unless the differences between the groups are huge. Okay, so in this case, D would be correct. The researchers probably did not have enough power to even reject the null hypothesis and to find a statistically significant difference. So using the same vignette here, we're going to look at a couple different answer choices. So which of the following conclusions would be correct here? Would be A, fasting blood sugar is a confounding variable. Would be B, whether the patients receive drug or not is the dependent variable. C, adding on a third group receiving a different dose of drug X would require use of ANOVA. Or D, fasting blood sugar is an ordinal variable. So, looking through these, the correct answer is C. Let's go through each of these and find out why they're correct or not. So 1, fasting blood sugar is a confounding variable. Well, it can't really be a confounder because fasting blood sugar is what you're actually looking for, right? So this is the outcome you're actually looking at. So in this case, this would actually be your dependent variable, right? Because it's going to be dependent on whatever group the patients fell in as far as the drug treatment goes. So this would not be a confounder. Now, could you say that maybe something like HbA1c was a confounding variable? Possibly. You could probably try to rope that into your analyses and see if that had a difference anywhere. But fasting blood sugar is actually what we're looking at as our outcome, so it can't be a confounder. Answer B, whether the patients receive drug or not is a dependent variable. That would be incorrect. We just said fasting blood sugar is a dependent variable because that's our outcome. Whether or not the patients got drug or not is actually considered to be the independent variable because we're setting that up. We put the patients into either group to get drug or no drug. So that's independent because we're the ones actually setting that. Okay. For D, again, the last wrong answer here, fasting blood sugar is an ordinal variable. It's not the case, right? This is a continuous variable because it goes from, the difference in blood sugar between 1 to 2 milligrams per deciliter is the same as 99 to 100. That's a continuous variable there. The distance between points is the same regardless of where you're at on the scale. So, and then another question you could ask was, okay, well, is blood sugar going to be a ratio or an interval variable? Well, can you have negative blood sugar? I don't think so. So 0 is significant there. So in those cases, that would actually be a ratio variable. Okay. So looking at the correct answer choice C here, adding a third group receiving a different dose would require use of ANOVA. That is true because again, if you just compare, a placebo to drug dose 1 and then do placebo to drug dose 2 and then drug dose 1 to drug dose 2, that's when you get into the multiple comparisons problem and you're more likely to make a type 1 error. So because of that, if you had a third group, you would need to use an ANOVA. So the next question, you're performing a case control study in which you are looking at patients who contracted measles versus control cases that did not, and then you're determining whether or not they were vaccinated. Which of the following statements is true? So A, this is an example of a prospective study. B, vaccination status is a nominal variable. C, this is an example of a randomized controlled trial. D, relative risk would be the best way to report the efficacy of the vaccine at preventing measles. Okay, so look at the study here. Think about what we're doing here. We're doing a case control study. And the answer here is actually B, vaccination status is a nominal variable. So let's look through that. So looking at this, this is an example of a prospective study. You know that's not the case because what you're doing is you're actually comparing groups of people that had measles, right, your cases, versus people that did not develop measles. And then looking back to see whether or not they were vaccinated. So because you're looking backwards in time, that makes it a retrospective study. So A is incorrect. C, this is an example of a randomized controlled trial. This is not the case. To make it a randomized controlled trial, you'd have to randomize individuals to either get the vaccine or to not get the vaccine, and then moving forward in time to see who developed measles. Right? So you have to start with your exposure and then go forward to see who has the outcome in question. So C is incorrect. For D, relative risk would be the best way to report the efficacy of the vaccine at preventing measles. This is not the case, right? Because whenever you're dealing with case control studies and you're looking retrospectively, you can't really do relative risk. You have to use odds ratios, right? You have to use things like the difference in odds. Relative risk is a form of probability. You would do that if you're using a prospective study. If you're, say, maybe doing like a cohort study or a randomized controlled trial, that would be a relative risk situation because you're looking backwards in time. Odds ratios are going to be better in that case there. Okay. But B, vaccination status is a nominal variable. That's true because, again, people either fall into yes, they're vaccinated or no, they're not vaccinated. And again, you can't say yes, one is more or less than the other. You may have your own opinions on that, but it's because it's just a yes or no sort of thing, and that makes it a nominal variable. In addition, it also makes it a dichotomous variable because there's not a yes, no, unknown. You'd have, because again, you probably would want to know specifically and correctly whether patients did get it or they did not. So that's why it makes it a dichotomous variable there. And then our last question here is you are performing a study in which you are randomizing 3 independent groups of patients, each with an N of 120, to either receive 30, 60, or 120 milligrams of oral pseudoephedrine, and then measuring mean changes in blood pressure. Which of the following is true? A, that performing multiple unpaired t-tests would lead to an increased chance of a type 1 error. B, the null hypothesis would be that the 120 milligram dose of pseudoephedrine would increase blood pressure the most. C, the means of measuring blood pressure does not need to be included in your results. Or D, a two-way ANOVA is needed to determine if you can reject the null hypothesis. And so the answer here is A, performing multiple unpaired t-tests would lead to an increased chance of a type 1 error. So let's look at the answers and see why they're incorrect or incorrect here. So B, the null hypothesis would be that 120 milligram dose of pseudoephedrine would increase blood pressure the most. That is incorrect. The null hypothesis would be that it doesn't matter if you got any dose, that it would make no difference on what you got as far as your blood pressure change goes. Okay, they would all cause the same difference. Now again, knowing what you know about drugs and how they affect the body, you know that, okay, well, that doesn't make any sense, but that is still how we have to define the null hypothesis. And again, if we did find that 120 raised your blood pressure more than 30, you could then reject that null hypothesis. Okay, so B is incorrect. C, the means of measuring blood pressure does not need to be included in your results. That's not true, right? You need to include how you measured it because, again, you want to make sure it's all consistent. If you're measuring blood pressure, via one arm versus another, sitting versus standing, those are all things you want to include. So again, the actual means or how you actually got your blood pressure measurements need to be included in the results. Okay. And then D, a two-way ANOVA is needed to determine if you can reject the null hypothesis. That is not true. You'd only need a one-way ANOVA. Two-way ANOVAs are good if you have multiple independent variables. Here, there's only one independent variable, and that's going to be the dose of Sudafed they got, right? Now, if we said, okay, we're basing it based off the dose of Sudafed they have, and then also whether or not they had pre-existing hypertension, that's a second independent variable you're introducing there, right? The dependent here is being blood pressure. But by introducing a second independent variable, that's when you need a two-way ANOVA. Here, you just need a one-way ANOVA because you have multiple groups, again, more than 2 groups. A is correct because if I were to continue performing unpaired t-tests, so I did 30 compared to 60, 30 to 120, and then 60 to 120, by doing multiple comparisons, you're much more likely to find a difference by just random chance alone, and so that's a type 1 error, right? You're rejecting the null hypothesis when no difference actually existed. Okay, so that's why A is correct. So that is the end of the review. Hopefully, if you have any questions, you review this, email me. I will be out of town before the test, but I will be there with you in spirit as some sort of blue force ghost over your shoulder, helping you to guide you to the correct answers. Again, you're all going to do great, but please, please, please review all the videos. If you have questions, try to get them in earlier. I know it's going to be tough this week with your exams coming pretty fast and furious there, but again, please do not wait to the last minute. You got to look at this stuff. Otherwise, it's going to look like just pure Greek on the test, and you don't want that to happen. Okay. So anyway, any questions, email me sooner than later. And I hope you guys have a great day, and I will talk to you later.